Hello, and thank you for your interest in using SPEGG. The first demonstration covered how to create your simulation class. That provides a broad outline for instructing your computer how to execute the code you will develop. Let's review our overview of how our SPEGG simulation can be structured. In the last video, we discussed how our simulation class can be set up. In this video, we'll discuss setting up the species object, which will be responsible for carrying out the key components of our eco-evolutionary simulation. Let's start by creating a header file that will define the species we want to model, which we've chosen to call demo species. Navigate back to the demo species header directory and create a header file for our species. So let's make a final demospecies.h. Demospecies.h will be populated as follows. We define our header file and remember the end if. We'll use the ins stochastic class as our base class from which the demo species object will inherit. I also want to anticipate two further classes at this point that we will make use of. First, we will be needing a class that keeps track of which individuals among our demo species are going to be parents. We're going to call this class demo species parents, and so we will need its header file demospeciesparents.h. However, we'll hold off for now on defining this class. The next class we'll need is a class that will be in charge of managing the offspring, including determining their genotypes. This is a generic SPEGG class called neonates class. Next, we'll want to create a constructor for demo species, which will use the arguments that are used by inStochastic. Namely, the current or starting number of individuals, which we'll call size val. The maximum number of individuals we can handle, which we'll call max size val. The random number seed, and the number of patches we'll simulate. We'll also have an add kids function that will handle reproduction and breeding, and an update function. For our update function, we have to clarify the namespace we're using, which is from our base class. This simulation won't have an environment class with which to interact, so we'll only make the updating functionality dependent upon our species class. Notice these are all public methods. This means that these functions are accessible from other classes. However, we want to have a few protected functions that are only going to be called within our demo species class. These are initialize patches, which will be used in the initialization regime, and a setPhenotype function that will manage our genotype-phenotype map. Now at this point, let's construct a skeleton of the corresponding .cu file that implements the functionalities we've defined for demo species. We'll navigate back to the src directory and create a .cu file called demospecies.cu. The first thing we want to do inside our .cu file is to include our headers. We'll of course need the class definition demospecies.h, but we'll need a few other header files. One header file we'll want to use is the header file that will define our genotype-phenotype maps called genotype-phenotype-map.h. The next header file we'll need is a header file for a class that will manage our updating function called updateBehavior.h. Both of these are standard SPEGG files, but, as I'll show in a bit, requires some degree of customization. Finally, we would like to use some thrust functionalities, so we'll include those as headers as well. These are the copy function that copies thrust vectors, the sequence function that populates a vector with sequential integer elements, and a fill function that populates a vector with a common value. Now let's spell out our methods for our demo species class. First, the constructor. We'll just copy the function and its arguments from the header file and clarify that we are inheriting the constructor from the inStochastic class. So the first thing we'll do is initialize everyone to be of age 0. This isn't strictly necessary. Sometimes you might want to define your starting age structure to represent values observed in the lab or in the field. We'll next call our protected function to initialize our patches, which we'll define later. Then, we will initialize the allelic values for each loci. Let's just for now assume they are normally distributed with mean 0 and standard deviation 0.1. To do this, we will call the drawGaussian function, which is a SPEGG function that will draw n different Gaussian random variables with a common mean and standard deviation. Next, we call the setPhenotype function that determines individual phenotypes according to their allelic values. And finally, let's assign a sex to everybody using an assignSex function. Now we can define several of the protected functions we just called. We'll start with the initializePatches function. First, let's set the maximum number of individuals allowed in a given patch, which we'll assume is simply the maximum number of individuals divided across all patches. In practice, you might want to vary the maximum number of individuals that can inhabit a given patch. Now let's assign the patch for each individual. We'll use a thrust_fill function again for this. The second function that we glossed over was the setPhenotype function. I'm going to defer this to the next demonstration video and go instead to the assignSex function. The function takes as its arguments the index of the first individual whose sex has to be assigned and the number of individuals to whom we have to assign a sex. We will create a thrust vector called newSexes that will store the value for each individual whose sex we need to determine. What we'll do is simply draw a value of 0 or 1 at random for each individual to determine whether they are male or female. We'll do this using the drawBernoulli function that will draw a Bernoulli random variable for every individual whose sex we need to determine. Finally, we'll copy the output of that calculation to the vector sex that stores the sex of every individual. Notice that we are going to fill in the values for individuals starting at the index of the first individual whose sex has to be assigned. And so you define most of the key terms needed to initialize your species class. Now, referring back to our header file, there are a few more methods we need to implement, such as the addKids method and the update method. But notice that these aren't involved in our initialization. So let's return to our genotype-phenotype-map class, because we need to define that in order to even initialize our demo species object. In the next video, we'll take a closer look at the setPhenotype function that implements the genotype-phenotype map. Thank you for watching, and if you have any questions, please shoot us an email via our mailing list, speg-users@googlegroups.com.